In October 2019, a confidential file appeared on a NASA server, only to be deleted moments later. But the internet never forgets. The leaked document contained a claim so terrified, and so revolutionary, that it threatened to upend the entire foundation of computer science. Google claimed they had achieved the impossible. They declared they had built a machine that performed a specific calculation in just 200 seconds. To understand why that number matters, you need context. For the world's most powerful supercomputer at the time, a machine the size of 2 basketball courts, to perform that same task, Google estimated it would take 10,000 years. Think about that scale: 200 seconds versus 10,000 years. This wasn't just a speed upgrade. This wasn't Moore's law. This was the difference between walking and teleportation. It was the Wright brothers' moment for the quantum era. But almost immediately, the celebration turned into a war. IBM, the rival giant, struck back. They accused Google of hype, lying about the numbers, and using a dangerous marketing term: quantum supremacy. So, where is the truth? Is this machine, which looks more like a golden steampunk chandelier than a computer, actually the key to the future of humanity? Or is it a billion-dollar science experiment that can't even run a simple spreadsheet? And if it does work, is the encryption that protects your bank account and national secrets about to be shattered? Today, we are going deep. We are going inside the dilution refrigerator, down to the atomic level, to review the most complex machine mankind has ever built. Welcome to the world of Sycamore. Chapter 1. The Golden Chandelier, the Hardware Review. When you search for quantum computer, you see images of a dazzling, intricate structure of gold and copper tubes, hanging in a dark void. It looks beautiful. It looks alien. But here is the first secret: that isn't the computer. That golden structure is actually a refrigerator. Quantum information is incredibly fragile. We are dealing with subatomic particles, and in the quantum world, heat is noise. Heat is chaos. If the environment is even slightly too warm, the magic breaks, and the calculation fails. So, this entire chandelier is a dilution refrigerator. Its only job is to step the temperature down, layer by layer. At the top, it's room temperature. By the time you get to the middle, it's liquid nitrogen cold. But at the very bottom, in that small, isolated chamber, the temperature drops to 15 millikelvin. Let me put that number in perspective. The empty vacuum of outer space is about 2.7 Kelvin. The core of this machine is 100 times colder than deep space. It is likely one of the coldest places in the entire Milky Way galaxy, right here on Earth, created by humans. And sitting right there, at the bottom of that frozen hell, is the actual computer. The Sycamore processor. It's small. It looks like a standard silicon chip you might find in a laptop. But the architecture is radically different. This chip contains 54 transmon qubits. Now, in a classic tech review, this is where I would tell you that more is better. But in 2019, during the historic run, only 53 of them worked. One qubit broke. It failed to operate. And yet, even with a broken processor, with only 53 working qubits, this chip managed to outrun the combined computing power of the entire planet. To understand how a broken chip beat a supercomputer, we have to talk about the coin flip. Chapter 2, The Power of 53, How It Works. The computer you are watching this on right now works on bits. A bit is like a coin on a table. It is either heads 1 or tails 0. It is certain. It is stable. But Google's Sycamore uses qubits. A qubit is like a coin that is spinning. While it is spinning, is it heads or tails? It's effectively both. It is in a state of superposition. It holds the probability of being heads and the probability of being tails simultaneously. Now, do the math. If you have 1 qubit, you have 2 states at once. If you have 2 qubits, you have 4 states. If you have 3 qubits, you have 8. It doubles every time. It's exponential. By the time you get to Sycamore's 53 qubits, the number of simultaneous states is 2 to the power of 53. That number is approximately 9 quadrillion. Imagine a library with 9 quadrillion books. A classical computer is like a librarian who has to walk down the aisle and check every single book, one by one, to find the answer. Sycamore. It doesn't walk the aisles. It exists in the entire library at the same time. It doesn't search for the answer. The The correct answer effectively emerges from the interference of probabilities. This is the power that terrified the tech world. But power is useless without a test. And the test Google chose was controversial. Chapter 3. The Supremacy Test, the benchmark. Google needed a task. They needed a benchmark that would humiliate a classical supercomputer. They couldn't use Excel, or Photoshop, or Minecraft. Those programs run on logic that doesn't benefit from quantum mechanics yet. So, they chose a mathematical problem called random circuit sampling. Imagine asking a computer to roll 53 loaded dice, millions of times, and tell you the exact complex probability pattern of the results. For a human, this is meaningless noise. But for a computer, it is a nightmare. As you add more dice or qubits, the math becomes so complex, so dense, that a classical supercomputer simply runs out of memory. It chokes. In 2019, Google fired up Sycamore. They ran the circuit 1 million times. The machine finished the job in 200 seconds. Then, Google's scientists turned to the world's most powerful supercomputer at the time, the IBM Summit. This machine is a beast. It has 9,216 CPUs and 27,648 GPUs. It consumes enough electricity to power a small city. Google ran the math and said for IBM Summit to do what Sycamore just did, it would have to run non-stop for 10,000 years. They published the paper in Nature. They popped the champagne. They claimed quantum supremacy. And that is when IBM kicked down the door. Chapter 4. The Titans Clash, the Controversy. 2 days after the leak, IBM published a blog post. The tone was academic, but the message was savage. They effectively said, Google, you are wrong. And you are arrogant. IBM argued that Google had intentionally rigged the estimate. They claimed that if you programmed the supercomputer smartly, if you used every hard drive, and every ounce of memory optimization, the IBM Summit wouldn't take 10,000 years. It would take 2.5 days, 200 seconds vs 2.5 days. Suddenly, the 10,000 years headline looked like a lie. Critics jumped in. They said if a classical computer can do it in 2.5 days, then you haven't achieved supremacy. Supremacy means the other guy can't do it. So, was Google lying? Was it all marketing hype? Here is the nuance that most mainstream news missed. And this is critical. Google was right about the trajectory. Let's assume IBM is right. Let's say the gap is only 200 seconds vs 2.5 days. What happens if Google adds just one more qubit? The complexity doubles. What happens if they go from 53 qubits to 60 qubits? That 2.5 days for IBM becomes years. At 70 qubits, it becomes centuries. Sycamore proved that the scaling works. It proved that we have found a machine that leaves classical physics in the dust. The exact number of days doesn't matter, the slope of the curve matters. But there is a catch. A massive, frustrating catch that keeps this machine in the lab and out of your home. Chapter 5. The Noise Problem, Why You Can't Buy One. If Sycamore is so powerful, why aren't we using it to cure cancer or mine Bitcoin right now? Because Sycamore is noisy. Remember that spinning coin? Imagine trying to keep a coin spinning perfectly on a table while an earthquake is happening. That is what quantum computing is like. Stray heat, electromagnetic waves, even cosmic radiation from space, anything can knock a qubit out of its delicate state. This is called decoherence. In the 2019 experiment, the accuracy of Sycamore was only about 0.2%. That means 99.8% of the time, the output was noise. But because they ran it millions of times in seconds, they could statistically extract the signal from the noise. This is the current era we live in. It's called the NISQ era, noisy intermediate scale quantum. We have built the race car engine. It has thousands of horsepower. But the steering wheel shakes violently, and the wheels fall off every 500 meters. To make this technology truly change the world, we don't just need more qubits. We need better qubits. We need logical qubits, groups of physical qubits that work together to correct each other's errors. And this race for error correction leads us to the terrifying question. The question that keeps security experts awake at night. What happens when we fix the noise? Chapter 6. The Encryption Apocalypse, Shor's algorithm. When people hear quantum computer, they usually think of two things: sci-fi teleportation, or the end of privacy? Let's talk about the second one, because while Sycamore is currently just solving random mazes, the architecture it validates is effectively a ticking time bomb for the entire internet. Right now, every digital secret you have, your credit card number, your medical records, your private DMs, and state secrets, is locked behind a wall called RSA encryption. The logic of the lock RSA relies on a very simple mathematical truth. It is easy to multiply two large prime numbers together, but it is incredibly difficult to take the result and break it back down into the original primes. If I ask you to multiply 7 times 13, you say 91 instantly. But if I give you the number 340 trillions, 282,366,920,938, and ask for the 2 prime factors, a classical supercomputer would have to crunch that for thousands of years. That difficulty is the wall that protects the modern world. The quantum key Shor's algorithm. In 1994, a mathematician named Peter Shor wrote an algorithm that terrified the NSA. He proved that a quantum computer wouldn't have to guess and check. Using the principles of superposition and wave interference, a quantum computer can find the period or repeating pattern of a function. By finding this period, the computer can mathematically derive the factors of that massive number incredibly fast. It turns the 10,000-year problem into a coffee break problem. The harvest now, decrypt later threat now. You might look at Sycamore's 53 qubits and relax. To break standard 2048-bit RSA encryption, we don't need 53 qubits. We need roughly 20 million noisy qubits or a few thousand perfect logical qubits. We are years, maybe decades, away from that. So, why worry? Because of a strategy used by intelligence agencies and hackers called harvest now, decrypt later. Bad actors are currently stealing encrypted data that they cannot read. They are hoarding terabytes of government comms, financial ledgers, and personal data. They are storing it in massive server farms, waiting for the day a machine like a scaled-up Sycamore comes online. The moment Q-Day Quantum Day arrives, all that stolen data from the past 20 years unlocks instantly. The secrets of 2024 will be readable in 2035. Sycamore didn't break the code yet, but it fired the starting pistol for the race to the code breaker. But here is the irony. While we obsess over destruction, the true purpose of this machine is creation. Chapter 7. The Simulation Revolution: Chemistry and Biology. In 1981, the legendary physicist Richard Feynman said something that became the mantra of this industry: nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. This is where Sycamore stops being a codebreaker and starts being a world saver. The problem with chemistry: we think we understand chemistry. We have the periodic table. We have labs. But actually we are terrible at simulating it. A simple molecule like caffeine seems basic. But to simulate the exact energy state of every electron in a caffeine molecule using a classical computer is almost impossible. The electron interactions are quantum correlations. The complexity grows exponentially. To perfectly simulate a modest-sized drug molecule, you would need a classical computer with more bits than there are atoms in the known universe. We can't calculate it. We have to approximate it. We have to guess. The Sycamore solution: because Sycamore is a quantum system, it doesn't have to approximate. It mirrors nature naturally. It can map the electron states of a molecule directly onto its qubits. Let's look at 2 specific examples where this changes human history. 1. The fertilizer problem: nitrogen fixation. This sounds boring, but it keeps half the world alive. Humans produce fertilizer using the Haber-Bosch process. It requires massive heat and pressure to rip nitrogen bonds apart. This single industrial process consumes roughly 1% to 2% of the world's total energy supply. It is a massive source of greenhouse gases. Yet, bacteria in the soil do this effortlessly at room temperature, using an enzyme called nitrogenase. Why can't we copy the bacteria? Because the mechanism of nitrogenase is too complex for our supercomputers to model. We can't see how it works deep down. A scaled-up version of Sycamore could model that reaction perfectly. If we unlock that catalytic process, we could slash global energy consumption and revolutionize agriculture overnight too. The next general battery, we are desperate for better batteries for electric vehicles and grid storage. Currently, finding new battery materials is a slow process of trial and error in a lab. Mix this, test that, see if it explodes. With a quantum computer, we could simulate the chemical properties of new electrolytes and cathode materials inside the processor before we ever mix a chemical. We could iterate through 1 million potential battery chemistries in a week. This is the promise. Sycamore is not just a faster calculator. It is a key that unlocks the source code of physical reality. The reality check, however, we must step back from the sci-fi dream. We need to be honest about where Google is today. Sycamore simulated a random circuit. It did not simulate a caffeine molecule, at least not fully. It did not break RSA. What Google demonstrated was raw control. They showed that they can manipulate these 53 finicky, sub-zero particles well enough to beat a classical supercomputer at one specific game. But learning to play one game is the first step to mastering the sport. In the next section, we have to look at the competitors. Because while Google was popping champagne over Sycamore, a different approach was being built in the shadows, one that uses trapped ions instead of superconducting loops, and it might just win the war. Chapter 8, The Quantum Format Wars. Superconductors vs. the rest. History teaches us a brutal lesson: being first doesn't mean you win. Betamax was first. VHS won. MySpace was first. Facebook won. The internal combustion engine wasn't the first car engine. Electric cars existed in the 1800s, but it was the one that scaled. Right now, we are in the 1980s of quantum computing. There isn't just one way to build a quantum computer. There are completely different religious sects of physics battling for dominance. And Google Sycamore represents just one of them. To truly review Sycamore, we have to look at what it's up against. We have to compare superconducting transmons against trapped ions and the dark horse, photonics 1. Team Google: the superconducting approach. Sycamore uses superconducting transmons. Think of these as man-made qubits. They are microscopic circuits printed on a chip, just like the processor in your phone, but made of materials that lose all electrical resistance when frozen. The pros: speed, they are fast. The clock speed of a superconducting qubit is incredibly high. This is why Sycamore could run that calculation in 200 seconds. Fabrication: Google knows how to print chips. The cons: the goldfish memory. These qubits forget their state instantly. Their coherence time is measured in microseconds. The fridge, as we saw, they require that massive, energy-hungry dilution refrigerator too. The rival trapped ions: IonQ and Honeywell. While Google is trying to build artificial qubits on a chip, companies like IonQ are saying, why build a fake qubit when nature gave us perfect ones? They use trapped ions. They take individual atoms, usually ytterbium, ionize them, and then trap them in a vacuum using electromagnetic fields. They levitate the atoms in mid-air and blast them with lasers to program them. The comparison fidelity in atom is perfect. Every ytterbium atom in the universe is identical to every other one. Unlike Google's manufactured chips, which have manufacturing defects, atoms don't have factory flaws. Memory: trapped ions can hold their quantum state for seconds, sometimes even minutes. Compared to Sycamore's microseconds, this is an eternity. But they are slow. Painfully slow. The verdict: if Sycamore is a Ferrari that breaks down every mile but drives at 300 mph, trapped ions are a reliable Toyota Camry that never breaks down but drives at 30 mph. 3. The dark horse: photonics. Then there is the third approach, using light. Photons. Photons have a superpower: they don't interact with the environment. You can shoot a photon through a fiber optic cable across the ocean, and it stays a photon. It doesn't get distracted by heat or magnetic fields. This means a photonic quantum computer theoretically doesn't need to be frozen. However, the problem is the same as the benefit: photons don't interact with anything, including each other. To build a computer, you need qubits to talk to each other. Forcing light to interact with light is an engineering nightmare. Why Google chose the hard path. So why did Google choose the superconducting route despite the noise issues and the giant fridges? Because of control. With a chip, the qubits remain stationary. You can wire them up. You can build control systems around them. Google is betting that they can engineer their way out of the noise problem. The quantum volume metric. This war gave rise to a new metric. IBM introduced quantum volume, a number that takes into account the count and the quality of the qubits. Right now, the lead changes hands every few months. Google announces a breakthrough. Then Honeywell announces they doubled their volume. Then a startup in China claims an advantage using light. But for us, the observers, this war is good. Competition breeds innovation. The fact that Sycamore has rivals is the best thing that could happen to Sycamore. Chapter 9, the roadmap to 2029 logical qubits and AI. So, what happens next? Google is not building Sycamore just to win a benchmark war against IBM. They have a public roadmap, and the deadline is fast approaching, 2029. By the end of this decade, Google plans to build a commercially useful quantum computer. But to do that, they have to solve the noise problem we discussed earlier. And the solution is brute force. The era of logical qubits right now. Sycamore has 53 physical qubits. They are noisy and error-prone. Google's plan is to group roughly 1,000 physical qubits together to form just one logical qubit. Think of it like a choir. If one person sings off-key, you hear it. But if 1,000 people sing the same note, the average sound is perfect. The crowd drowns out the error. Google wants to build a machine with 1,000 logical qubits. Do the math: 1,000 logical qubits x 1,000 physical qubits, each equals 1 million physical qubits. We need to go from the 53 qubits you see in Sycamore today to 1 million. In less than 10 years. The AI convergence. How do they manage a system that complex? This is where the story comes full circle. They will use AI to build the quantum computer. And then, the quantum computer will build the next AI. Google DeepMind is already using AI to optimize the cooling systems and error correction codes for Sycamore. We are approaching a singularity where these two technologies merge. Sycamore is the hardware, AI is the conductor. When they finally sync up, the rate of human progress won't just accelerate. It will go vertical. Chapter 10, the final verdict. So, let's go back to the question we started with. Did Google Sycamore break physics? Is it the most powerful machine ever made, or just a useless science experiment? The honest answer is, it is both. As a consumer product, Sycamore is useless. It can't run Doom. It can't open a spreadsheet. It is a 54-qubit calculator that gets confused by heat and noise. If you judge a fish by its ability to climb a tree, Sycamore is a failure. But we aren't judging a fish, we are judging a revolution. Go back to 1903. The Wright brothers' first flight lasted 12 seconds. They flew 120 feet. It was pathetic compared to a bird. It was useless for travel. You couldn't carry cargo, but that 12-second flight proved that heavier than air flight was possible. It proved the physics. And less than 70 years later, we landed on the moon. Google Sycamore's 200 seconds is our 12-second flight. It proved that we can manipulate the fundamental fabric of reality to process information. It proved that the multiverse of possibilities we call superposition can be harnessed by human hands. We are currently living in the vacuum tube era of quantum computing. Sycamore is our ENIAC. It is big, clunky, and fragile. But the transistor is coming. The microchip is coming. And when the quantum transistor moment arrives, the world we know, our encryption, our medicine, our materials, and our understanding of the universe will change forever. The door has been opened. And there is no closing it now. History is being written in code and cold atoms, and most people are sleeping through it. But if you've watched this far, you are one of the few who wants to see what's coming next. This is just the first entry in our investigation into the future of computing. If you want to understand the technology that will define the 21st century, from the AI wars to the quantum revolution, you are in the right place. Click that subscribe button to open your access to the quantum files. I'll see you in the next deep dive.